So if you were here on Thursday or listened to the lecture on YouTube, you learned about what it means to be soluble, what it means to be insoluble in terms of what's actually happening with the molecules. Today we're actually going to talk about the concentration, so units of concentration and how to use those in conversions. And then we're also going to talk about solution stoichiometry. So stoichiometry is once again just converting from amounts of a particular reactant or product to another reactant or product. And then we're going to use solutions in limiting reagent problems, which, so that's just an extra thing that you might see on the exam. So I'll let you all write that down. I see a confused look. Okay. Let me know if you can't read anything. Stoichiometry, S-T-O-I-C-H-I-O-M-E-T-R-Y. Stoichiometry. This Thursday is the last day of new material, so you just have, I think, 2 weeks of material on this exam. What? Yeah, for the whole semester, yeah, and last day of new material for the whole semester. Thursday. All right. So concentration is the amount of solute per amount of solvent or solution. In salt water, can anyone remind me what the solvent is? Water. Solvent is the main part. It is always liquid. So solvent is what things are dissolved in. Solute is the minor part. It can be solid, liquid, or gas, but it is dissolved in the major component. So in this case, we have a concentration is how much of, for example, salt is dissolved in salt solution or dissolved in water, okay? One of the units of concentration we use is mass percentage. And mass percentage is the mass of the solute over the mass of the solute plus the mass of the solution. Sorry, mass of solvent times 100%. So you're saying out of that entire solution, how much is the solute? You can also write this as mass of solute over total solution mass, right? Because solute plus solvent is total solution. And just like every other percentage, you multiply it by 100%. Bless you. And I will go through an example of how to calculate this. Are we still writing? Yeah, we've got, okay. Solute is my name is good though. Yeah. You could like, it's almost the entire thing. All right, let's do an example of this. I could say 27.5 grams of NaCl is dissolved in 175 mils of H2O, and that H2O has a density of 1.00, grams per mil. Okay, so in order to determine the mass percentage, what do I have to do with that volume? Convert it into mass. You have to convert it into grams. So the first thing I'm going to do is going to take 175 mils of H2O, and that is 1.00 grams per mil, which just gives you 175 grams. If you do that in your head, that's cool too. Just want to walk you through that. So now we have the mass of our solvent, and we also have the mass of our solute, so we can do our mass percentage calculation. So we're going to put 27.5 grams of NaCl over 27.5 grams of NaCl plus 175 grams of H2O. The most common mistake that's done here is forgetting to put the NaCl on both the top and the bottom. So what a lot of people might do is put 27.5 grams of NaCl over 175 grams, but no, you have to, the bottom is the total mass of the solution, so you have to add them together. Just like if you were taking the percentage of males in this class, you would say, okay, there are like, how many, like 52 guys in this class over 105 people, right? So that means that you've added what you put it over, you've added both the males and the females. So the answer would be, if you, you need to multiply it by 100%, and it gives you 13.6% NaCl. Any questions thus far? Just to make sure that you have this down, I'm gonna give you a practice problem that's gonna be a little harder, but it should be the same process that I did right here. Yeah, Anna. How do you know I know you have yeah, I just gave you the density. I provide it for you and you use it. Yeah. Yes, so in this case, you would get 27.5 is 3 sig figs, and then you would add 27.5 and 175, you'd be specific to the ones place, it would still be 3 sig figs on the bottom too. Question. And you assume 100 is infinite sig figs. Okay, so what is the mass percent of NH4Cl if I dissolve 10.0 grams of it in 190 mils of methanol? Now, methanol has a density of 0.792 grams per mil. So in this case, it's not going to just be 190 grams. You have to do the conversion of 190 mils to grams of methanol and then do the mass percentage. So please do that. We're not going to spend too much time on this because we have a lot to cover, but I do want to make sure that you can do this calculation. Okay. What's my first step? Convert milliliters to grams using my density. So I'm going to take 190 mils of methanol. And 1 mil of that weighs 0.792 grams, which gives you a total of, where's my math? 150 grams of methanol, 149 for something, but if we do sig figs, it's 150. Then we take 10.0 grams of NH4Cl over 10.0 grams of NH4Cl plus 150 grams of methanol. And I got 5.3%. You might have gotten something slightly different if you didn't round the number of grams of methanol, but it should be about that. You got 6.2? Okay. 6.2. 0.2 or 5.3, depending on where you rounded it. And if you round that, I will definitely account for that on the test. So either one of those answers would be acceptable. Now we can use this mass percentage as a conversion factor. So notice in mass percentage that you didn't need to use your molar ratio, okay? I mean, sorry, your molar mass. So just because you have grams of NH4Cl doesn't mean that you're going to have to turn that into moles of NH4Cl. Sometimes you will, but in terms of mass percentage, if I give you grams of something, all you have to do is divide it by the total mass. All right. Using mass percent as a conversion factor. If a soft drink is with a density of 1.04 grams per mil, is 11.5% sucrose, what volume of soda contains 85.2 grams of sucrose? Now, it's important here that you distinguish the solution from the solute. So what is the solution? The soda, yeah, the soft drink. What is the solute? Sucrose. Okay, so what you're going to do in terms of using the mass percentage as a conversion factor is you're going to assume that it's per 100 grams. So if you have, so you're going to assume 11.5 grams of sucrose per 100 grams of soda. So first off, just take a look at that 11.5 and say, oh, we're going to assume that it's 100 grams of, we're going to just put it over 100 grams so that we can convert from grams of sucrose to mils of solution. And note that any density I give you in this type of problem is density of the solution, okay, of the liquid solution. So I'm going to go from 85.2 grams of sucrose, and the 11.5 grams of sucrose goes on the bottom here, right? Because I need to get rid of those grams of sucrose and instead go to 100 grams of soda. Now I can use my density of the soda, 1.04 grams per 1 mil of soda. And that gives us 712 mils of soda, which is not quite a liter. $712 mils. So it would be 0.712 liters if you convert it into liters. If I ask just for volume and don't specify a volume unit, you can do it in mils, you can do it in liters, I don't care. Any questions on this? I'm going to have you all go in the opposite direction, okay? So I'm going to give you a volume and you're gonna have to go to grams of solute, but, so does everybody have this down? No? Okay, just. Okay. How many grams of glucose are in 25 mils of aqueous solution if the solution has a density of 1.09 grams per mil and is 19.6% glucose? I would like you all to try that. Raise your hand. Are there any words that I need to write better? That's a 1.09 grams per mil. So it's like the last conversion I did, but it's going in the opposite. All right, so my unit map here is I'm going from mils of solution to grams of solution to grams of glucose. So if I start with 25 mils of solution, what conversion factor will I use to get to grams of solution? Density, okay? So I'm going from, I'm gonna use 1.09 grams of solution per 1 mil of that solution. And what do I assume goes on the bottom there? 100 grams. So 100 grams of solution and 19.6 grams of glucose on the top, which gives us 5.3 grams of glucose. Any questions on that? So they're normal conversion problems. You just have to be really careful that you know what you're talking about in terms of grams of what, grams of solute versus grams of solution, and also that you know how to make that percentage into a conversion factor, which you just put it over 100. Do we want to move on to molarity? All right. Does everybody have this down? Okay. Molarity is the most common concentration unit used in chemistry. If you go on in chemistry and biology, you will use molarity. And so molarity is abbreviated as M, but M stands for moles of solute over liters of solution, which means when you use it as a conversion factor, you're going to use it as moles over liters. So the M is moles over liters. what is the molarity if 15.5 grams of NaCl are dissolved in 1.50 liters of solution? What's the first thing I have to do? To get moles over liters, convert the mass to the grams to moles using a molar mass. So I'm going to use 15.5 grams of NaCl, and the molar mass of that is 58.44 grams per 1 mole of NaCl, and that gives me 0.265 moles of NaCl. Now I take 0.265 moles of NaCl over the 1.50 liters of solution, which gives me 0.0177 moles per liter, or molarity. I will accept you writing the answer in either form with your unit. It can be M or moles per liter, but you have to know that they are equivalent. Okay, so I will often give you a concentration that's like 1.5 M, and you have to know that's 1.5 moles per liter. Any questions so far? So here I found the molarity of a compound. Yeah. You got a different answer? I might have kept a couple extra sigmas. Yeah, that's fine. Or you might have kept a couple extra sigmas. Wait, 0. Yeah, I got 0. No, you're right. Sorry, I thought you meant, yeah. I miswrote it. It was right in here, but not up there. There you go. But the 0.176 versus 0.177, that's just a rounding. So 0.177 moles per liter. Now, I just found the molarity of the compound NaCl. However, when you dissolve things, what do they do? When you dissolve ionic compounds, what do they do? They split into their ions, okay? So you can find the concentration of individual ions within that compound as well. For example, if I have MgCl2, this dissolves into Mg2 plus and 2Cl minus, okay? So for every MgCl2 I put in, the ions that are created, 1 Mg2 plus and 2 Cl minus, which means that the concentration of MgCl2 I put in will be doubled for Cl2, Cl minus, because I have 2 of them for every MgCl2 put in. So for example, if the molarity of MgCl2 is 1.0 molar, the molarity of Mg2 plus is also 1.0 molar because it's 1 to 1, but the molarity of Cl minus is 2.0 molar. And I'll do a conversion to prove that to you, but does everybody kind of understand where I'm going with this? Like if I had 2 MgCl2? Yeah, then I would have 4 Cl. It'll just be double what you have of the MgCl2, and I'll show you why in this conversion. So I'm going to clear this. I could say, what is the concentration of Cl minus if 10.0 grams of MgCl2 is dissolved in 2.2 liters of solution? Ten point oh grams of MgCl2. I'm going to turn this into moles of MgCl2. Okay? So 1 mole of MgCl2 weighs 95.21 grams. And normally, if I wanted to determine the molarity of MgCl2, this compound, I would stop here with the number of moles and then divide that by the volume. However, I want Cl minus. So what I'm going to do is I'm going to use my molar ratio. So 1 mole of MgCl2 gives me 2 moles of Cl minus. And now I've doubled the number of moles, which gives me 0.210 moles of Cl minus. Divide that by moles. Divide that by 2.2 liters. That gives me 0.095 molar Cl minus.
Can you just keep it as one?
Yeah, you can keep it, but you have to use a placeholder 1. Because I'm dividing. That last step is dividing. So you can keep it as one conversion as long as the last step you divide by 2.2 liters. Don't multiply by 2.2 liters. You're welcome to do that. So because I use my molar ratio, and it's a 2-to-1 molar ratio, when I dissolve MgCl2, it would be like 0.048 molar MgCl2. But if I'm specifically talking about Cl minus, because for every MgCl2 there are 2 Cl minuses, it's double the concentration. So I might ask you that. Only convert it into concentration for the ion if I specifically ask for that. Is everybody good? Yeah? Okay. Let's talk about solution stoichiometry. So I'm drawing out this map again, but this time I'm going to liters on the bottom. So you can use this for almost any stoichiometry problem as long as you just have it go to different units. So grams of A, we're going to use molar mass. I'm going to go use a different color for that. We know we use molar mass for our grams. And we use our molar ratio to get from moles of A to moles of B. And what do we use to get from moles of A to liters of A? Molarity. because it's moles per liter. So we just have a different conversion factor that will get us to a different unit from moles of A or B. I'll let you write this down, and then I'll go on to a problem on the next slide. How are we doing? Good? Okay. So last week I had to do reaction stoichiometry where I went from grams of a compound to grams, or grams of a product to grams of reactant, or vice versa. But that doesn't necessarily make sense if you are using solutions, because you're not going to weigh out a solution. You're going to measure a solution in terms of its volume, right? You're going to use a volumetric flask or a beaker or something like that. So it's more common if you have an aqueous solution that you will start with volume and then try to get to grams of your product. So in this case, what type of reaction is this? There are two types: precipitation and double displacement. The one that's important is precipitation, because I'm going to end up with grams of something, but I'm going to start with volumes. So I would say, how many grams of the precipitate are formed when 910 mils of 0.83 molar, bless you, Na3PO4 react. And we're going to assume that the other reactant is in excess. What's my precipitate? Calcium phosphate. Okay, so what you're trying to get to is grams of calcium phosphate, but I might not say calcium phosphate. I may say the precipitate, and you have to identify what the precipitate is. So based on my little unit map I had for you there, the conversion map, I'm going to start with milliliters. Never start with molarity. Why should you never start with molarity? One unit over the other. So you want to start with the volume because it's an amount, and then you'll use the conversion factor. So molarity is a conversion factor. Don't put it first. So we're going to go from mils. Where should we go from mils? Liters, because we need to get to liters to go to moles. So we're going to use mils to liters to moles of Na3PO4 to moles of Ca3PO4 2 to grams of Ca3PO4 2. So that's my unit math. Any questions on how I got that? I'm going to start with my 910 mils. What am I going to use to get from mils to liters? 1 liter is 1,000 mils. And sorry, I need to label what I have, Na3PO4. Sorry about that. Now, I'm going from, my next step is liters to moles. What do I use? Molarity. And I need to break it up into moles over liters. Do not put M over liters, put MOL over liters, okay? So in this case, I have my molarity is 0.83 moles of Na3PO4 per 1 liter. We always assume 1 liter on the bottom. I wouldn't, molarity is always per 1 liter, just like density is always per 1 mil. Yeah. Now I use what to get to moles of Ca3PO4 2? Molar ratio, which is 2 moles of Na3PO4 to 1 mole of Ca3PO4 2. And then I use my molar mass, which is 310.18 grams per 1 mole of Ca3PO4 2. So if you look at your conversion map that we wrote on the last slide, you'll see that we went from the bottom left corner, liters of A, through molarity to moles of A, through our molar ratio to moles of B, to our top right corner, I guess for you would be this top right corner, using our molar mass to get to grams of B. And we get 120 grams of Ca3PO4 2. If you do the math, you'll get 117, but why did I do 120? Sig figs. What limited my sig figs? I have 2 things that limited my sig figs. 910 and 0.83. Those 2 things, I gave those to you. Those are not exact. Those limit your sig figs. Questions on this? All right. You can also use solutions in limiting reagent and theoretical yield problems. I'm going to run through a quick one, and then we'll do the worksheet. I do want to give you a little extra time on the worksheet because it's kind of a longer one. It's just 1 page, but it's got 5 problems on it. Everybody have this down? Okay. I'm going to use the same reaction. Ten 10.0 mils of 0.32 molar CaCl2 reacts with 19.0 mils of 0.18 molar Na3PO4. What is the limiting reagent and theoretical yield in grams of the precipitate? So once again, this is a theoretical yield problem and limiting reagent problem. So you need to do two calculations. First, I'm going to start with CaCl2. I'm going to go with 10.0 mils of CaCl2. I have to turn that into liters. So 1 liter is 1,000 mils. And for every 1 liter, we have 0.32 moles of CaCl2. For every 3 moles of CaCl2, we have 1 mole of Ca3PO4. And as I told you before, the molar mass of that is 310.18 grams for 1 mole of Ca3PO4. And that gives us 0.33 grams. It's 2 sig figs. Why? The molarity, 0.32. Moving on to the next one, 19.0 mils of Na3PO4. I'm going to turn that into liters. For that, the molarity is 0.18 moles of Na3PO4 per 1 liter. It's a 2-to-1 ratio here. And the same molar mass. And that gives us 0.53 grams. What's my theoretical yield? 0.33 grams. That's my TY. What's my LR? Calcium chloride is my limiting reagent. Excellent. So I just ran through this really quickly because I know we've been doing a lot of limiting reagent, but I also want you to be able to do this if you see it on a test. Know that you can start a limiting reagent from volumes of solutions. Or you could even start with a volume of a solution with grams of another reactant and go 2 grams of a product. Any questions? All right, we're going to start the worksheet now.
Not so much more to the kids.
I know, I'm like trying to fit everything into one line here.